Okay, so it's my great pleasure to introduce our speaker today, who's Clement Asperger. Clement has no stranger to was here last summer. He has been working with us. He's been co-supervising Maddie, and so he's been so was Felipe actually, who has so and Berkeley Dehan as well. Clement is was a professor at Berkeley University, now chief scientist and co-founder of Mantle Labs. And he's going to tell us about some really amazing work they've been doing on using self-supervised learning for creating representation map to crop. So we're really looking forward to this. Clement, it's all yours. Thank you.
Yeah, thanks, Keshav. Thanks for attending. I'm very sorry that I couldn't make it, but I need to be here for the family. But I hope we can still engage in a good discussion. I wanted to share with you, let's say, the progress we made over the last year in terms of, using the Barlow Twin to really map what happens annually, because you can always produce nice maps of AGB or crop types, right, for a single year. But for scalability issues and for our, let's say, area of interest as a company, it's very important that we have this kind of possibility to work over tens of years, right? Especially when it comes to above ground biomass in forestry. Before I dig into the details, I just wanted to show you a bit in which market we operate. So at Mantle, we cover all these kind of buckets here, from grassland to rice to forestry. So in forestry, we do conservation, but we also do afforestation and regen ag. And we cover here the voluntary carbon market. So contrary to the compliant market, it's really voluntary, as the name suggests. So people invest in NBS, nature-based solution projects, but you need good monitoring and verification solutions, because there are a lot of issues in this market, unfortunately. And we want to help to solve these issues so that the market can really take up, so that we get better products, right? More products. And I think the solution to this is having a higher integrity of the projects, while at the same time bringing cost down, but also energy footprint. Because perhaps in the discussion we can discuss, perhaps one of your questions might be, why don't you use another model? And usually they tend to have millions or billions of parameters. Our self-supervised learning pipeline is very parameter scarce, if I might say so. We have only 41,000 parameters. So in terms of energy footprint, I think that also helps. Now, I will illustrate most of this AGB stuff in reference to ARR projects. So it's reforestation projects, it's planting trees, mostly in an agricultural context, so agroforestry projects. And there we have a kind of old label, which was VM47, if I'm not wrong, from Vera. And now the major companies in the US, they just recently said that in the future going forward, they require to run projects only under this Abacus label, where we are also involved in terms of a company since a long time with our partner Amazon. Just to explain you what Abacus is in this kind of projects where people plant, let's say, cacao and shade trees and so on degraded pastures. So we have to solve for the issue of leakage, for example. So there will be no leakage allowed, meaning if you have a pasture and now you have some cows on this pasture, if you just use this piece of land to plant trees, the cows will be grown somewhere else. So this is what is called leakage. And the projects will have to make sure that there's no leakage liability. So there's no displaced production. So you need to estimate also the leakage, right? The second main pillar, I would say, is all about eligibility. So you don't want to have incentives in any way that farmers first cut down trees and then earn carbon credits by planting new trees. So there will be no deforestation allowed in the prior 10 years before the project start. And this also shows you why historical time series are so important, because you need to go back then for the full 10 years to show there was never a tree cover. If it's a secondary cover, there are some exceptions, right? So you need also to track the age of the forest and so on. And then there's obviously this baseline, which means instead of saying, okay, I measure only the biomass at T0, so at project start, and I just assume it's a horizontal line going forward, what you do is really a matching against counterfactuals. So each of your project plots, you match against 30 to 100 counterfactuals. And I will show you how we do this later. Then you need in this dynamic baseline, obviously, to calculate the above ground biomass or kind of stocking index. And you need to compare the performance of your plot against the counterfactuals. So this gives you the degree of additionality, so which can vary between 0% and 100%. So if for some reason your counterfactuals also increase the biomass, right, this would be deducted from your project, because everything is greening, so you would subtract this, and this is covered by this additionality. So as you might have already understood, this carbon quantification or AGB estimation is really central in many of these aspects. I don't read them now all, you see them here on the screen. Obviously, we can't only do AGB. I mean, we have in our portfolio many other offerings that are listed here to be really able to process projects under this new Abacus label. So if you are a bit in the field of above ground biomass, you think directly about GEDI, and we also use GEDI, which measures the full waveform in a sparse spatial sampling. It measures something like relative heights, if you think. So it's not really the height of the canopy as shown here, but it's a combination of height and density. I think, Andrew, you are not muted. We take this also as a reference, but what makes really the difference for us is what we use as predictor variables, right? And here people traditionally use either, let's say, cloud-free images if they find some, or they use some kind of gap filling, or they use what we call maximum value composites or composite images. And we will use something completely different, as the title suggests, our self-supervised learned representations. I will explain in a minute. So the core idea is that for each pixel, you have to assume that we have this kind of information at the basis. At the basis, if you would put a sensor on the ground, right, a multispectral sensor, you would be able to acquire each day, right, one spectral signature. And if you would plot this daily spectral signature over time, you would get kind of this surface. And this kind of surface here we call spectral-temporal signature. This is the optimum case. In reality, beside all these atmospheric effects and radiometric calibration of the sensor, in reality, we don't observe any every day. I mean, already the Sentinel, for example, passes by only every 5 days. So you have only a 5 daily revisit. And then from time to time, we have also coverages. So it's very difficult to get this spectral temporal signature, because the data is very messy, very cloudy. You know, you have these sensor stripes and so on. But what we developed also with you, so Keshav, Maddie, and Andrew from Cambridge, is this self-supervised learning model, which we call the Barlow Twin, which takes such spectral temporal signatures. If you see my mouse, So this would be here a spectral temporal signature. Here it's just shown as a 2D matrix. The white lines here just indicate some missing data due to cloud coverage.
Your
And
mouse.
now,
Sorry, we can't see your mouse.
okay, no problem. I'm looking here at the left-hand side, right, where you see this matrix with some white lines. The white lines indicate missing data or clouds. Now we take this for really literally hundreds of thousands of pixels for the learning phase. But what we do is for each pixel, we create at least 2 augmentations. We create many more, but imagine we have only 2, right? And this is shown a bit more to the right. You see 2 temporal subsamples. So from this corrupted matrix at the left-hand side, we create 2 augmentations, 2 smaller matrices, which have no clouds, right? And we pass them through the encoder to generate representations. And then the representations we pass through another projector to create what we call embeddings. Now, the beauty of, or the work that the Barlow twin has to do is simply to make sure that the embeddings of these 2 augmentations are as similar as possible, as similar. And if you would, an easy way to see if they are similar is just to calculate the cross-correlation matrix. There you want to make sure that each element of the embeddings is perfectly correlated, right? So from the top part and the lower part, so you have on the diagonal values close to 1. And the different embeddings you want to be independent from each other, meaning the correlation should be close to 0. And this you achieve by using the loss function, which is indicated. So again, to summarize very quickly, you create augmentations and you make sure that the Barlow twin learns from these augmentations identical embeddings and then also identical representations. Once the network is trained, you apply it to your messy and corrupted data, pixel by pixel, right? And you get these gap-free representations shown on the button. Now these, let me show you, before I show you some representations, this is, let's say, as a function of epoch, how the values out of the diagonal tend to move to 0, and values on the diagonal, they move towards 1. This is the learning. This is what we want to see. Ideally, we want to have really all values of the diagonal at 0 and on the diagonal at 1. Okay, so in essence, once you have learned this and you apply this to your time series, you can choose whatever length of the time series you want. We use typically 1 year. So roughly we would have 70 images, but as I said, 50% or more might be cloudy. And then we pass them through the Barlow twin and we get these representations. In our case, we get 32, but this number is not fixed in stone. It can be any number. We did some trials to find for us the best number, and it was 32. And here is a random combination of these, of 3 out of 32 representations. And what you immediately see is how rich the information is. It's really a very good learning of this spectral temporal signature. You readily see the field boundaries. You see different colors indicating a different spectral temporal behavior of different crops. Obviously, over agricultural fields is often more different than over forests, right? Forests have less variability between them compared to crop types. But each color that you see here would represent a different crop type or a different phenological development of this crop. And if you would think about a forest pixel, you would see differences in species, difference in stocking index, differences in density, height, etc. Okay, so this is the compression. By the way, we store this information as 8-bit, so which has the additional advantage that instead of storing hundreds of images, each having 10 spectral bands, we now have to store only per year, let's say 30 representations, each in 8-bit. So it's a huge reduction also of storage cost, if you think from a kind of company perspective. Okay, in principle, you can use these representations and recreate spectral data. We do not recommend this, but in principle, you can generate RGBs for any day in the year. So here's the 1st of January over huge areas. So you would not find a 1,000 kilometer by 1,000 kilometer area gap-free, right? And anyhow, the sensor strip is only 300 kilometers large, but you can synthetically generate it using another neural net based on these representations. But we don't do this. What we do is we use them directly for our downstream applications. If the downstream application is a crop type classification, we use the representations to identify crop types. And here in this talk, I wanted to show you how we use them for AGB, so in forest. So here comes again the GEDI that I mentioned already. The GEDI measures these relative heights. We take a difference of the relative height at 95 and 10% percentile. This is our label, our target, right? And then we take our 32 Barlow twin representations as predictor variables. And then we have here kind of fully connected feed-forward neural network with 3 hidden layers. You see here the specifications a bit. I mean, there's a lot of additional information that we tweaks to make it really work better. But this is the basis information that I wanted to share with you. And now we can create based on these representations and a model trained on the GEDI. We can then generate here these relative height maps in very high spatial resolution, so 10 meter. It's very consistent also across space, and as I will show later, also for historical extrapolation. So what do
I said here about the previous slide, please. The RH slide you said about GEDI. I mean, it wasn't clear to me why the representations work so well for relative height with GEDI. I mean, what is it about the spectral temporal information that correlates with relative height?
Yes, I mean, I have some slides at the very end where I did a kind of radiative transfer model simulation to show this. Perhaps we can come back to this in the discussion, right? It's anyhow, it's not simply a height information, it's height and density, and height and density correlates with above ground biomass, but also the foliage, etc. So there must be some indirect link to the spectral data. Otherwise, we would not see any correlation between spectral data and these relative heights. And the variation that these relative height differences induce in the spectral reflections are picked up by the Barlow twin representation, and therefore we are able to model this. Because if you would compare, let's say, these modeled, what you see now on my screen, this modeled or estimated tree canopy height, it's not really tree canopy height. I don't like this word because it's really the difference between 90% relative height or 95 and 10%, but it's proportional to height and difference. So now when I say historical extrapolation, what I mean here is we really in the company, we use only 1 year of data to train this model. So both for the Barlow twin part and for the GEDI model part, we train only using data from 2019, yeah? Because in 2019, we have Sentinel-2, but we have also GEDI. And we train this over, let's say, the parastate of Brazil, using a spatial subset, obviously, only. And then we freeze the model. We really freeze it. We don't touch it again. We don't even do a fine-tuning, nothing. We freeze the model, and then we apply it to all the years. So let me show you how this looks like. So this is now for the years where we have Sentinel-2, so 2017 to 23. If you see, now this is 2017. Now, the more it gets dark, dark means here it's low height, yeah. So deforestation, you see clearly here the pattern of deforestation starting from existing deforested areas, moving then out. So we checked this a bit with a data set which is called the Do Plantations, also in Brazil. So using the same model, again, not retrained. And for this data set, what is reported is the planting year. And for example, in this example here, all these plots that you see were planted in 2017, yeah? And you see nicely that our estimated AGB seems at least plausible to say, right? Same here, we then manually delineated some stable forest, some pastures. So you see, obviously, it met, again, these are just plausibility checks, right? So it looks how it looks, should look like. Here we have manually found some plots where we know they will be deforested, and you see exactly in which year apparently the deforestation took place. And we have also some, let's say, test polygons where we are sure there was some forest gain happening. So this is still all about Sentinel, but Sentinel does not give you the 10 years that I'm talking about. Sentinel was only launched, as you know, or is only available since 2017, yeah, the A and B. So what we did here is again, it's the same Barlow twin trained on Sentinel data of 2019, and we just apply it to the Landsat imagery, right? Obviously, we removed the bands which are not available in Landsat. You know, perhaps that Landsat does not have these 3 red edge bands, so those were removed, but the rest is the same. And we apply this model without any retraining to the Landsat data. And you see, I mean, it's not perfect, but it's almost perfect. You have also to consider that Sentinel comes at 10 meter and Landsat has a coarser spatial resolution. So part of this scatter is also a result of differences in spatial resolution. Now, if we freeze,
what's the graph showing? Is it AGB?
No, in this case, it's still this relative height difference. To AGB, I will come. This is just a simple conversion that we apply later on. Sorry, David, this is still this relative height difference. Yeah. Okay, and then again, we apply this PROSE model to another year, let's say 2018. Beside the spatial resolution differences, you will have really difficulties to find any significant differences. So you can use this Sentinel trained model, trained on 1 year of data, and feed in Landsat, and you get very consistent results. So this is for 2018. Again, you see it's nicely scattering around the 1-to-1 line. And indeed, when we calculate the difference between, let's say, 2019 and 2018, so the relative height difference between these 2 years, you can't even distinguish these 2 lines. There are 2 CDFs here, the one from Sentinel-2 and the other from Landsat, and they perfectly match. So if you would calculate a kind of forest loss based on this index, right, you would get for a region very much the same values. So, and this is
question about when you say apply the model to Landsat, does that mean that you take a subsample of non-cloudy Landsat images and you apply that to the frozen encoder model?
Yeah, so we don't do any training for Landsat specifically. We train only on Sentinel in 2019. And then instead of feeding in, when we do the scoring, when we do the map production, we just feed in Landsat data. We could feed in Landsat and Sentinel. This will be our future, right? We will always combine the 2 to have really the densest time series. But here to show the working, we feed then really in only the 16 daily or 14 daily Landsat observations in the same manner as we would feed in the Sentinel-2.
But it's a random subset of non-cloudy images.
No, it's really pixel by pixel.
With each pixel, it will be a randomly chosen set of days with non-cloudy pixels.
Exactly, exactly. So we use typically 11 augmentations per pixel. So what you see here is the average then of 11 augmentations per pixel. And each, yeah, as you correctly said, Keshav, each augmentation is a temporal subset of non-cloudy observations.
Thank you.
So if we subtract these two relative height differences, we get forest loss and gain in terms of height, yeah, or relative height. So you see these many black spots. This is only between 1 year and the next. So you imagine how dynamic this landscape in Para is, how much deforestation we have. It's shocking. I mean, this black is too much in terms of area. And you see the same black here in the Landsat. So you would see the key takeaway message from me is whatever you use, if you use Sentinel or Landsat, if you were interested in deforestation, you would equally well see it a little bit better in Sentinel because you have a higher spatial resolution and a more dense time series. But we can use Landsat as well, which is fantastic because it allows us to go back 10 years and more. And this is what we need for our projects. So coming back to David's question, that was all this relative height. Now to convert this into above ground biomass, we have essentially two solutions. One would be to use a few on-field measurements, right? The other would be, and this is what we followed, just to assume, okay, in the neotropics, what is a typical above ground biomass of an old forest, right? Yeah, in this environment. And what we found in the literature, it's only literature, right? It's roughly 350 tons per hectare, as you see in the graph here in the center. And now we simply assume that the highest value that we get in terms of the height, yeah, corresponds to this 350 tons. So it's a simple scaling. It's here almost a factor of 10. To be precise, it's 9. So we just scale our original stocking index by 9 to get above ground biomass in tons per hectare. Now, this gives you now the AGB over 11 years here, starting from 2013 to 23. Soon we will be able then to do this also for 24 in tons per hectare. And if you look at some stable forests, they look like this. If you see some deforested pixel, they look like this reddish line, etc. So here are all the 11 maps together. Just to point out, because you might say, I have seen something similar already. I don't think so, because this area is huge now. This is more than 300 by 300 kilometer each map. And so this is, yeah, more than a single tile. And you don't see any striping of orbits, etc., or hardly. Perhaps it's not that perfect, as I always claim. But let's say it's really a very good and historically consistent product, partly built only on Landsat and partly built on Sentinel, but really having only used 1 year of GEDI data. I need to emphasize this again. We only used to produce this 2019 data of GEDI. So now you know right now, for example, there's no GEDI. So if you don't have these consistent predictor variables, like we have the Barlow twin representations, you would have problems to make a map for 2024, because right now we don't have any any GEDI reference measurements for this year. Okay, that's this part. Perhaps here kind of detail or zoom in that you get a bit impression how this matches well what we see in a very high resolution imagery. Now, to the validation, we have a problem we don't have, but perhaps we can talk about this later, how we can collaborate to do a better collaboration. We had only available this data set here. So this is from our project in Parastate, where for roughly 40 different agroforestry plots, they did some field measurements, right? So they delineated 30 by 30 meters, and then they used classical field inventory to estimate AGB. Now, the problem is we were not able to, because the GPS devices they used were not precise enough to give us exactly the location of these 30 by 30 meter plots. Sometimes they had one plot, sometimes two, sometimes three plots per farm. So we simply assumed, okay, let's take what we have and assume this is representative for the entire farm. So what I want to say is on the y-axis, you should add a large error bar, because if there are only 3 plots and the farm was heterogeneous, then this average that we show here might be quite far away from the true average. And for our product, we took all the pixels in the farm and we average. So overall, we have an RMSE of less than 30 tons per hectare and R square of above 0.6. If you compare this, for example, with the Meta product from Facebook, which you all saw probably in the past months, right? You see, I hope you see the difference. So here the R square, using exactly the same approach, right, is only 0.15 compared to what we had. So we have clearly the best product out there, and we have an annual product. So, and we can go back 10 years easily. So we use this here for eligibility. As I said, we need to make sure that our project plots are not located in recently deforested land. We use it also, I forgot to mention this, perhaps I should spend a second on this. So we estimate also the age of a secondary forest, because in Brazil, you are allowed to cut down your forest if your forest is a secondary forest, and if it's a young secondary forest. I think the age limit is 5 years, if I remember correct. So therefore, we need also to track the age of the secondary forest. We use this same AGB product to do project stratification, because when we select the counterfactuals, we have to do it by stratum. So we first stratify our projects. Typically, we generate 2 strata. Let's say pasture and what we call chiquera, so some regrow. So you see it here on the left-hand side. What is black is really the pasture, very low AGB, and in white, then a higher AGB above a certain threshold. And we use the AGB also for the counterfactual selection. The counterfactual selection can be visualized as this. Imagine here in the center of this circle, of this disk, you have your project plot. Now we are supposed to look for the 100 best matching counterfactuals around this, taking into account, I don't know, they should be in the same ecoregion, etc., not in protected areas, etc. So we proceed here in 2 steps. First, we use the Barlow Twins to pre-select. So we do a matching. So we calculate the Euclidean distance between the Barlow Twin values of our project plots and all the million of pixels around. And then we find the closest match in this spectral-temporal domain of the Barlow Twins. This is our pre-selection, and then we apply the AGB for the final selection. So perhaps for one project, this might look like here shown. So on the left-hand side, you see what we select based only on the Barlow twin representations, and then on the right-hand side, the final selection, taking into account the AGB as well, and here the same for a different project plot. It's clear we use this then also, we don't have real, the project only started now, so we don't have real projects, but these are some agroforestry plots for which we know the age of the plantation. So going forward, we will then monitor for each of these projects or project plots and the evolution of the AGB after T0, so after planting. And having the counterfactuals in yellow and the project plots here in green, we see how much additionality we have. So what would be converted into carbon credits is this difference between your baseline, your dynamic baseline, the orange lines, and what you achieved in your project by planting trees. Okay, I come to my last slide. So I hope I was able to convince you that we have a good solution to leverage really long time series, thanks to the Barlow twins that we developed together with you. So in principle, we can go back really to the start of Earth observation in 1972. And this is great because all this data is now freely available. So anyone who says, I will launch in the future a fantastic new satellite, you know, in the market, he will need still a solution to go back in time, because it's not sufficient to just track what is going on now. I hope I made it clear. All the labels out there and all the projects always require a view back in time. So you need Sentinel and Landsat and a solution to calibrate models, let's say, in a sophisticated manner. Good. Perhaps in the discussion, I will come back to this question, what is really learned, but let me take a break here first, and we take some questions. Thanks very much for listening.
Okay, so people in the room can ask questions. If you're online, just unmute yourself and ask a question. Anybody? Amelia?
I was curious about I had a couple of questions. One of them was about the choice of this RH95 minus RH10 metric. I was wondering, did you try any other metrics and did they work as well?
Sorry, I could really not hear you that well. I just understood the last point. Did you try other metrics? But I'm not sure if I really fully understand what you are referring to. Can you repeat, please?
Yeah, are you able to hear me better now?
Yes.
I guess I was wondering if you tried other metrics besides RH95 minus RH10 and if the performance was good.
Ah, okay. We made a few tests. For all this, we made a few tests, but really not a good one. I mean, we tried 2-3 variants also for the relative height. And once we saw the results, we said, okay, this is sufficient, but we did not do an elaborated hyperparameter tuning. For the Barlow twin, the same. For the GEDI model, the same. We tried 5-6 different settings, and then we settled quickly, because this is all now used for production. We are really in this production phase, and we need to produce outputs, and unfortunately, we don't have the time. So yeah, we are happy when we have a bit more time to use and try different combinations of relative heights. But we compared it, for example, against, let's say, the 98, and it was a bit better. It doesn't also make that much of a difference, but it was a bit better, and therefore we settled for 95 minus 10.
Got it. Okay, thanks. And then I guess you talked a little bit about validation, and I just had some thoughts about other validation that maybe you've considered and said we can't do this, but some ideas. One of them is like other deforestation products to I think the Hansen forest loss or the JRC forest loss or the MAP biomass forest loss, which would all cover PADA, might be interesting to compare against. And then I was also wondering if you consider doing validation of years 2020, 2021 through 2023 against the rest of the GEDI catalog. So you could look at where GEDI shots fell and see what your model projects as the height metric there and see how they compare. And I was wondering if you considered
Yes. Yeah, thanks. So let me start with the last point. This we did, right? I did not mention here. And therefore we decided we can really freeze the model. As I said, we had more years available in principle for the GEDI, but then we saw, when we freeze it, it's almost identical then compared to reusing new data or predicting what GEDI sees in another year. So this we did, and therefore we are quite confident that this is a kind of universal relation that we find for this ecosystem, at least parastate, right? So our Barlow Twin against the typical GEDI in this region is so stable that we feel confident to be able to apply it to the 10 years. Now, for these other validation data sources, we tested them all. But I mean, I guess you have also your own experience with this. Hansen, I mean, if you look in all these in a little bit in detail, you probably agree they have more shortcomings than something else, right? So Hansen himself, he said I think in a disclaimer that his product should not be used in the context of our projects or the type of projects. And really, if you look into details, the same for the JRC map and for map biomas. So we looked them all. We are confident. I have not prepared a slide set for this, but we see clearly that we do not only outcompete this product from Facebook, but also all what you mentioned, clearly. And none of this would be anyhow able to fulfill the requirements of the Abacus label. So what we need is really measurements. Really, the existing products, we are really confident that we are far better than any existing product. What we really lack is, let's say, field measurements. So most of the stuff we do is plausibility checks. So an undisturbed forest should have a stable or slightly increasing AGB, right? And if you know there's a plantation, you want that it grows. All this is for me just plausibility. It's not really a validation. But yeah, it's hard to find good validation data. Mm-hmm. So we had only this chrono sequence, and there it did not work too bad. So for the Abacus label, this is fully sufficient. They want just to tell you how relaxed they are. They just want to have a kind of stocking index which is proportional to your AGB. So they don't care how strong the relation is, but just, let's say, related. So in this we clearly achieve here.
Okay.
Thank you. Yeah.
I have a question, Kevin, related to your last Amelia's question. Like, I think the major product of GEDI is canopy height, or the difference of the relative heights. And it's the information is sparse signals, right? It's only a footprint, like across the globe. It's not a wall-to-wall mapping. It seems that what you have shown to us is like a wall-to-wall mapping from the regression of the like Landsat or Sentinel optical images to have a wall-to-wall mapping of this AGB. So how do you get that, like to calibrate those optical signal directly to a wall-to-wall mapping of AGB?
Yeah, so the Barlow Twin representations we have derived only from, let's say, Sentinel time series at 10-meter resolution, wall-to-wall. As you said, Jihan, the GEDI points are only sparse, right? Every 60 meter in one line, and then the lines are 600 meters apart. So we just pick matching points, right? we do a kind of pre-selection. Let me show you. So we exclude somehow here, so we exclude border pixels because you know the GEDI points, they have also a geolocation error, which is quite significant. So by calculating the standard deviation in a moving window, right, we avoid those pixels here which lie on the border of two classes. So we screen a bit in addition to the typical normal screening of the GEDI points according to the flags. We do an additional screening to make sure that we take only pure GEDI points for training. Yeah, and then imagine you have in an area 1 million matching points of GEDI and the Barlow Twins. Then we build this simple 3-layer, 5-layer neural net to predict this GEDI relative height difference from our Barlow Twin representations. And then we freeze the model and we apply it to the wall-to-wall Barlow Twin representations. Did this answer your question?
A follow-up question, like, even though I think it's just a canopy height, it's not AGB, right?
Yes. So it's a relative height, and it's more than a relative height because it's a difference of two relative heights, right? So as I said, 95 and 10. And then we just assume that the highest height corresponds to the densest vegetation. So this is just based on literature that we found in the neotropics. A typical value for an old-grown forest is around 350 tons, yeah? And if our highest relative height is, let's say, 35, right? Then you would have a scaling factor of 10. We have a scaling factor of 9. So we just multiply the output of the neural net by 9 to convert this relative height into AGB. But then the validation that I showed you, right? That was really tons per hectare. So you saw there was almost no bias, right? There was a scatter around the 1-to-1 line. The slope of the line was not very, very different from 1. So apparently this simple conversion works. What we also tried is to use the AGB product from, I think this is a level 4 product of GEDI, but we found it did not work better than this simple conversion. Perhaps let me answer this question that we had about what is really learned, because I've done some simulations. So sorry, it's very tiny, the font. I hope you can read it. What I did is I took a radiative transfer model. So it's based on physical equations, and Yang worked with it. And I simulated the spectral signatures during 20 years for 49 different forest stands. So each stand I parameterized a bit in a different way. So what I enter is a kind of typical growth behavior of 49 different forest stands. One is shown here, only 1 out of 49. So what I input is an evolution of stem density on the top height, top left, the tree height, the crown diameter. You can read yourself. All these biophysical variables, they enter into this radiative transfer model, yeah? And I did this day by day, 20 years, yeah, times 365. And you see for one stand here in blue, what I entered into the radiative transfer model. Now, the radiative transfer model converts these biophysical variables into spectral reflectances, here for 10 spectral bands. So again, what is shown here is only for 1 out of the 49 stands, yeah? And you see how the different spectral bands react to this temporal evolution of the biophysical variables. Now, based on this, I took a 5 daily sample, assuming I have a kind of Sentinel-like sensor, and I added 70% cloudiness, which is huge. This is probably the worst we have. 50% is quite normal. 70% is really a lot of cloudiness. So I corrupted this data. Again, as I said, I have daily, but I took only every 5 days, according to the Sentinel overpass. And then of those 5 daily, I corrupt 70% of the observation by cloud. And now I apply the Barlow twin, or let's say kind of version of the Barlow twin, to these annual time series. So I did the same as I tried to explain during my talk. I take 1 year of data and I take augmentations, and I learn the representations from these augmentations. And what is really fantastic is these 49 stands, they naturally cluster. So what is shown here are 3 out of many representations. Yeah, each dot is 1 year of data, and each color is one of these 49 stands. So all what is yellow here on the left-hand side is 1 stand, and you should see, let's say, 20 dots because I have 20 years of data. So you see already that the Barlow twin and any spectral-temporal method learns apparently these differences in structural variables, biochemical variables that characterize a forest. What I did also, I looked for each of these 49 stands where they lie in terms of the overall distribution. So each black dot here is one of the 49 stands. And then, for example, if you look on the top left, what you see in red are then 20 dots of stand number 1. So again, the same information as before, they naturally clump, and this in all bands, so in all representations. And importantly, I can use now these representations to estimate the biophysical variables. So I can go back to the input. You see, it's not perfect, but it has learned something from this spectral data that relates back to the biophysicals of the stand. I hope it was clear.
Yeah, I think it's very good. I'm afraid we'll need to probably stop in a minute or two. The next group wants to use this room. David, if you have any questions, perhaps you could take that offline with Clement, but let's thank Clement again.
Perfect. Thank you.
Thank you.
Mike, and I'm sorry to have to bring this to an end. I had some questions myself, but we'll just take that offline. Thank you very much, Clement.
Yeah, you're welcome.